NMRs and IRs in them, okay? And if they need GCMS, but most likely IR and NMR. Okay, so this next part is going to be nucleophilic addition. This is going to be to polar pi bonds, and this is going to have reagents that are going to be strongly nucleophilic. So that actually be the first part of this nucleophilic addition information. So right here we have a double bond, and so when we attack across the double bond, what is that called again? That's addition, right? And so we're going to be talking about attack across this double bond. So remember that this is a non-polar pi bond. These ones are going to be the ones that we've already mostly done, right? You may remember that we'd already talked about that quite a bit. So what's the difference between a polar pi bond then? So non-polar one, no poles, right? A polar one, though, has poles. It has a positive and a negative end. The carbon typically being the positive end. Usually this is oxygen up here, right? More often than not. So what else does this add to this addition mechanism? Well, you can attack these ends, can't you? Okay. So for example, if you have a nucleophile, which end will it attack? Carbon, right? The electron 4 one. Does anybody see that we're actually kind of going back to material you've seen before? We did a lot of nucleophilic attacks at carbonyls, don't we? Yeah. In this case, though, we're instead of just having it come back or do something with like a proton, we'll actually do an addition. Technically, the proton is an addition. So, again, remember that this pi bond here tends to be relatively electron rich. It tends to react with electrophiles. This end right here is going to be electron poor. That's that positively charged carbon. And so that's going to tend to react with nucleophiles. And so we can do a 1-2 punch, as it were, on our carbonyl double bond. So these are some of the different reactions that we've seen with polar pi bonds. This was chapters 18 and 19, actually, right here, where we had ketone aldehydes that we did reactions with. If you're ever looking for these other ones, these are chapters 22 through 23, right here, that has these as the leaving group. And those are the carboxylic acid derivatives. Okay. And then these ones are the imine and nitrile. So those are all going to be ones with polar pi bonds. Notice that there is an option to have a nitrogen polar pi bond. It's a little bit more unusual, but you still will see it quite a bit, especially in things that are biological molecules. Okay. So this is the general mechanism for a nucleophilic addition to your polar pi bond. So again, we have here electron poor. And so you'll get a nucleophile that'll attack down here at this carbon, which is the electron poor carbon, right? And then the electrons are going to go up onto this oxygen, and that's going to make that oxygen there very electron rich, right? And so now we have that relatively unstable oxide, okay? And so you're going to have something that's electron poor. Protons are very common, so you can get no H, especially in biological systems. It's probably the most common way this happens. And then you're going to donate the proton, move the electrons onto the proton, leave behind the conjugate base, and that's a proton transfer to finish this reaction off. And so we've done an addition of H and whatever our nucleophile was across this bond, haven't we? Okay. All right, so this nucleophile can be attacked from either side of the carbon's plane here in an amine. So we could attack it from this side, which is coming out towards you, right? We could attack it from behind, coming back through the plane. Everybody see that okay? So either side can be attacked, either from the top or from the bottom, right? So when you do these attacks, you can actually end up with a racemic mixture. If you have an asymmetric structure, these won't be 50-50. Okay, if you have a symmetric structure, they'll be 50-50. Okay. If you guys notice, this is basically a recap of rules that we've talked about before. There's actually very little new information that's going to come along for the rest of the course. We're more like working old information, so you guys have it better shaped and understand it better. Okay, so these are going to be substituent effects on this and the relative reactivity of these. So right here we have a carbonyl. It has no other substituents. We just are going to substitute an OH on here for our addition. And so in each of these cases, we're using the hydroxyl group here as our nucleophile. And so what you're going to see here is this one right here has a relative rate constant of 3 times 10 to the 6th. And it's pretty fast, right? And once we substitute a CH3 on here, what happens to our rate constant? It goes down quite a bit, doesn't it? Okay. And so if we look over here, what happens to our rate constant here? Drops off a lot, doesn't it? Yeah, it dropped off a huge amount. Okay. So remember that this carbon has that pi bond above and below, right? And so you need to attack it from where these CH3s are, essentially, don't you? Okay. And so this first part of this mechanism is really an SN2 style mechanism, isn't it? Okay. So you have a positively charged group that you attack with a nucleophile, and it can attack from the opposite side of what would have been your leaving group in an SN2, right? Your leaving group in this case is going to be that pi bond. Okay. And so it's really the same sort of mechanism as an SN2. It's just you don't actually have the carbonyl leave, right? The carbonyl goes to an oxide. Okay? Or another way of thinking of it is your double bond is the leaving group. Okay? All right. Can everybody see those okay? Okay, very good. All right, so this is going to be your ketone here. This steric repulsion here from these two R groups and the ketone is going to make it much more difficult to attack from this side. The other part of this issue is that you actually are going to be in an equilibrium in this case. And this is going to destabilize this species here. So it has a lot of steric strain between these OHs and these R groups because you're very packed around this. And so this is actually going to cause the equilibrium to shift towards this side. And that's actually what you're seeing right here. This is those final states, right? So this is both disfavored kinetically, but is also disfavored thermodynamically. Okay? And so you actually get both effects working here. Right? Isn't that nice? Finally, they're working together. You can see both of the effects working at once. All right, what if we remove one of those substituents? Well, that would give us a hydrogen here. Notice that's a lot less sterically strained. There's also more room to approach over here, isn't it? And you're not blocking off that entire approach. Okay? And so it is both thermodynamically and kinetically more favored. Okay, here's some different examples of this. You will notice that the greatest concentration of positive charge, the most intense blue, is actually on this one right here. And so that gives you your greatest positive charge on the carbon. Over here, as we substitute, we're actually going to notice that we reduce the amount of positive charge that's on this carbon right here. It goes to a lighter shade. Okay? And that's because each of these CH3s is going to donate electron density, isn't it? That's that same inductive effect that helps stabilize carbocations, right? Okay. And so the ketones are more stabilized by the inductive effect than aldehydes would be, and then free carbonyls would be even less stabilized. So this is a more stable group than these. Or another way of saying it, this is more reactive, right? A little bit less, even more less reactive. Okay, so these are the hydride reagents. You may remember these from previous chapters. These are very, very common in these additions to a carbonyl. So you're going to see these a lot more even. And so this is sodium borohydride, and this was that BH4 that you may remember. And if we remember hydride, that was the H minus, right? That's actually what hydrides were. Okay. And so these are sources of H minus in solution. So this is the lithium aluminum hydride. This is another very common hydride source. Note again, it would be an H minus. That would be a hydrogen atom that has an extra electron on it, meaning it has 2 electrons, right? These are very common hydride sources. Keep in mind, these are very, very, very reactive, okay? Not something you want to sit around on a shelf. It will go away after a fairly short period of time, right? Okay, so why would we need these things to do these reactions? We were doing OH before. It seemed to actually be working pretty good. Well, if we use hydride, then it's a much more powerful nucleophile, isn't it? And so we can overpower what had been previously a very difficult to perform reaction. So here we have our ketone. We put a very powerful nucleophile in this time, and we can overpower that disfavored ketone going into our addition, right? And so we get the hydrogen substituted on here. You'll also notice that the hydrogen being here actually has less steric hindrance as well, doesn't it? It's less sterically hindered than OH would have been. Okay. Now note that these are the overall sort of abstract conditions. You'll have your hydride source, and then you'll finish it off with water, which will act as an acid. Okay. To protonate this oxide. This is much more specific reaction conditions. So for example, you would use something like lithium aluminum hydride, and then you'd put it with ether, you'd reflux it. That would perform the reaction where you would form the oxide, right? And then you would need to add something that's going to act as your conjugate acid. Okay. For example, this right here, these conditions would then give you the H on this oxide here, giving you the OH and finishing the reaction up. Okay. Okay. And notice we get yields of 83%, 80%. This will be racemic because, again, you can approach from either side of this. So it can come from the top or the bottom. All right, so this is benzaldehyde, and this is off of the benzene ring here. And so again, you can use a hydride to go ahead and do the addition for this. This one is sodium borohydride in glycerol. And that will give you at 80 degrees Celsius, 100% yield for this. Okay. The glycerol is going to be your source of protons in that case. Is there any reason we can't just throw hydride in with water, by the way? So water would actually react with our hydride, right? Hydride's a pretty good base, okay? And so the hydride would react with the H plus from the water, form hydrogen gas. Okay. So we need something that's not a very good acid if we're actually going to try to do this with hydride. In this case, it reacts so fast with this, we don't really have to worry about the glycerol as much. This is the lithium aluminum hydride. This is in THF. We'll finish it off with a little bit of acid with H2O. And this is going to give us, again, 100% yield. So this is a sort of simplified mechanism for that reaction. We've sort of dropped the sodium borohydride part and just recognized that that's really just a source of hydrides, right? So we put hydride here to start it off. That's the H with 2 electrons and a minus charge, right? Okay, and so we're going to go ahead and attack. Notice it's very similar to an SN2 style mechanism, right? The only reason it's not a SN2 is it's not substitution, right? We don't actually have a group that leaves. We have a double bond that leaves. All right. And so you're going to attack that carbonyl carbon here. This pi bond is going to go up onto the oxygen. That's going to give you the oxide. And then that's going to attack a hydrogen, pull the hydrogen over, and form the OH. Base will then leave as OH minus. and that's your proton transfer step. This almost essentially always comes from the solvent, and that's actually one of the reasons you usually have a second step where you add a solvent that's more acidic. Okay. All right, so this right here is your simplified mechanism for lithium aluminum hydride. You'll notice it's the exact same thing because they're just hydride sources, right? Okay. Let's test your understanding real quick. Why is HCl over here, by the way? So see how it's HCl with water? Yeah, it's for the hydronium ion. And it's because this is a little bit more acidic, so it can help push this over. Okay? Because this can actually stabilize that OH, the O minus a little bit. So it helps it push it the rest of the way. You could technically get away with using just water here, but you may not get quite as good of a yield. And you could use other weak acids. Okay, so this is actually your detailed mechanism if you were to look at this borohydride transfer. So here's your ketone. This is your borohydride. And this, we're actually doing the borohydride as borohydride, right? The BH4 with a negative charge. Okay, we're not just saying it's a source of hydrides. Okay, so what it actually does is it doesn't put hydride in solution. That's not how that actually works. It's a very useful, very easy mechanism that you can do everything else with very nicely, and it gives you all the information you usually need. But in certain cases, the difference matters. Okay, so this is the actual detailed mechanism of that. So you'll get the borohydride. The hydrogen bond here is going to go into a bond with this carbon, the positively charged carbonyl carbon. The electrons that are on the double bond, the pi bond, are going to go in a bond with the boron here. And so this is then going to come up as BH3 off of that oxygen. And so that actually stabilizes that oxygen, the oxide. And so the next part is you add your solvent here. That is going to give its hydrogen into a bond with this bond that was between the oxygen and boron right here. And then the oxygen-hydrogen bond is going to go onto the boron. And so what you'll end up having is the OH is then bonded to the boron here, the BH3, and you're left with the OH alcohol here. Okay? And that's actually the final finishing part. Now, if you had messed up and didn't put like water in here or did something interesting, it would have some meaning, right? You'd have slight difference here. As in, like, your product would not actually be the oxide, it would be the boron on here. Okay? Okay. So the lithium aluminum hydride, this is much more reactive than the sodium borohydride. So if we were to look at this on alcohol, for example, we would see that if you put this in with an alcohol, this reaction is extremely fast. And it's going to leave you with the AlH3, you'll make hydrogen gas, and then you'll deprotonate whatever alcohol you have. Okay? Now, if you do this same sort of reaction with the sodium borohydride, it's less reactive because this is not a metal, right? It's boron, so it holds on to electrons a bit better than the aluminum would. And so this is actually a very slow reaction as long as you don't take your sweet time isolating this and do it at a normal lab level of isolation. You'll get almost all of your product without being deprotonated and forming hydrogen gas. The greater concentration of the charge of the hydrogen is actually the difference here. So your aluminum here has a larger partial positive charge and a smaller, it has a larger negative charge on the hydrogen here. And that's because of the electronegativities. So boron has a pretty close electronegativity to hydrogen, right? Just a little bit less. Okay. The aluminum, on the other hand, because it's a metal, is going to have a larger, a smaller electronegativity, a larger difference of electronegativities with hydrogen. Okay, meaning the hydrogen is more negative with the aluminum. and so it is more reactive. All right, so let's look at the hydrides for the amines, excuse me, and nitriles. Does anybody want to try saying that with me? Amines? Yeah, be careful. So, amines means no double bond here, right? Amines is with the double bond on the nitrogen. Okay? So you gotta stress the I. Imine. Everybody want to try it again? Imine. Okay? Notice the amine with the A, right? Unfortunately, in English, those are extremely similar. All right. So this is going to be sodium borohydride, and what we'll see here is we'll attack the carbonyl. Sorry, amine carbon right here. That's the one with the partial positive charge for being in the double bond. The double bond will move up onto the nitrogen, which will then react with this second condition here, which donates the hydrogen to create the amine. Okay? Notice that's a secondary amine. This one right here is lithium hydride and diethyl ether, and so it's going to end up with the same sort of product at the end. You'll finish it off with water. This one gives a 92%. This one gives an 83%. Notice the big differences here tend to be whether you're an aldehyde or ketone. The aluminum hydride tends to be a bit more reactive, but you got to watch out for that because it also will react to anything with hydrogens on it. So if you have an OH or an NH, you could strip the H's off. You got to be careful, especially the OHs. Those are a big one. Nitrile, this is your nitrile right here. That's that CN. You notice that's like the cyanide group, right? So cyanide being substituted on something. So this is your lithium hydride and ether again. What's going to happen is it's going to attack that partially positive carbon right there. This is going to give it the substituted hydrogen on the carbon. We'll leave you with the negatively charged nitrogen. Note that this has a very high probability of going ahead and doing this reaction again. So you have a double bond here. You still have a partially positive carbon here. You can actually end up attacking that again and getting a double hydrogen substitution, especially if you have lithium hydride, which is very powerful. Okay. And so you'd end up with a -2 charge on the amine. Then you put water with it, and that would protonate that amine. Yeah, anybody have any questions there? No? Okay, so let's look at sodium hydride real quick. So sodium hydride is a very strong base, but it's actually a poor nucleophile. It doesn't attack as well. So if you use sodium hydride here, what you'd actually see is, you remember our E2s versus our SN2s? Well, that same behavior is going to show up on this because it has the same mechanism as an SN2, right? And so if you have something that's a better base instead, it can actually take the hydrogens off of that alpha position, right? And that would start a sort of E2 mechanism. Everybody see it okay? And so you would take the hydrogen off here. That would give a negative charge here. And that would be the setup for some sort of like E2 sort of mechanism. If you were to put water to try finish this reaction off, you just resubstitute hydrogen back on there with maybe a rearrangement happening. Okay? And so you'd actually not accomplish anything, or you get some random rearrangement to the more stable carbanion, right? Okay. This right here is going to be the nucleophilic addition. Because this is a poor nucleophile here for the NH, NaH, you are not going to actually get this nucleophilic addition. This reaction is going to be much faster. Okay, this one's going to happen preferentially. So let's predict the major product of the reaction shown right here. Okay. You all go ahead and start writing that out. I'm actually going to use the restroom while you guys start writing that out. Kind of crazy morning.